is for the lawyers. Okay, so real quick, I want to talk about sort of how things are changing as a function of time. So a little bit of history, then talk about what I'm trying to do today, which does involve OpenMP.
Hey, Bob, swing a mic over.
Okay, this is a tether. And then just talk about what maybe you guys can do for me in the future. Okay, ancient history. So there are a lot of really old codes out there. And if you think back in 1964, a NASA review panel noticed that multiple people were trying to write structural analysis codes and thought this is silly, we should have one. So they organized one, hired contractors, released it in 1968. The company Ansys that Bronis mentioned was founded in 1970. Some guy at Westinghouse named John Swanson was working on nuclear reactors for outer space, and he wanted to write some software. And they told him, like, we're Westinghouse, we don't do that nonsense, go back to work. So he quit and wrote the code himself. I'm an electrical engineer, so I think SPICE is important. That was first presented in 73. The DYNA 3D is the predecessor of LS-DYNA, so that started in 1976 at Livermore. And Abacus, another engineering code, started in 1978, some Brown professors. And so this is Michael's idea. We should have some contemporary pictures to remind people what the world was like. So the Beatles came to the United States, Elvis mounted a comeback, people walked on the moon, some companies were started. And then just for fun, younger people in the audience might be wondering why the pictures were black and white. Calvin asked that question and was informed the film was color, of course. The world was black and white. Anyway, the funny thing is these codes. Oh, one other thing is I haven't visited Livermore in a while, which is Bronis's fault. But the last time I was there, they had a code that predates my birth. Someone said in, I think, 1957 or 58, hey, there's this new thing called Fortran, let's give it a try. And last I heard, it was still around. It maybe migrated to C, but it was still around and still doing useful things. I mentioned that to a guy from Chevron, and he said, oh, we ported to Fortran when it became available. So there's a lot of really old stuff out there, going back to 50s and 60s, and it's still around. Yeah, that begs the question, how can that be? Surely, someone would have written something new by now. And so, my tether, I can't really see. So one obvious thing is, these old codes are still solving problems, right? So why would you get rid of a useful tool, right? There's many decades of labor invested in writing these things. So who wants to throw that away and reconstruct it? They don't exist by themselves. They're in complicated workflows. So if you want to replace a part of it, you may have to replace more of it. In the case of LS-DYNA, most of our input decks are made by tools created by our competitors. But our customers like them, so we have to live with that. There are generations of people who've learned how to use them, and we get all really cheap academic licenses, so more are coming. Some of these codes, like the original Ansys code, started out in the nuclear reactor business. So there's a lot of regulatory stuff, and those regulators require continuity. So they're not just market constraints. And finally, the code started a long time ago, but they're constantly growing and evolving. So they're and hopefully improving, of course, right? So even though the code started a long time ago, there's still code being typed in today. Anyway, so let me drill down a little bit into DYNA 3D, which is what led to LS-DYNA. So in 1976, Livermore, they wanted to do a three-dimensional high-energy, model of like imagine you drop something on the ground, right? Is that bad or not? There's a big G-force when you hit the ground. Can you simulate that? There was no tool they could use in 3 dimensions, so they had to write their own. And they did what anybody else in that time frame did. Is you do sort of one finite element at a time, run down your sequential processor or your CDC 7600 at a time. And that cartoon on the right is a pretend beam, right? So if you have, 3D elements, bricks, then you've got 8 corners and 3 degrees of freedom. So 24 by 24 array is one, this is the space for one finite element. They bought a Cray 1 and were horrified to discover that this code didn't run any faster on the Cray 1 than it did on the 6600 or 7600. And so someone thought, well, I have to wrong button. I have to transform this group of elements into groups of independent elements where, there are no equations shared. So you color them, and then you can sort of transpose them, and a Cray vector can run, one operation on every element simultaneously, well, in the pipeline. And then you can do the red ones, and you can do the green ones, and go back and forth. And by basically rewriting the code to transform all the basic data structures, you turn this into a SIMD code, and it ran much faster, and had a huge impact. Then if that code continued at Livermore for, I don't know, probably 2 decades, certainly one. And so that meant these, eventually Crays came with, 2 processors, 4, 8. And so, I don't know exactly what, in that time period, I played with Cray macro tasking, then micro tasking, then auto tasking. I'm sure the guys at Livermore did the same thing. Okay, so 1988, imagine if you're the guy who wrote that code. Oh, the French government came to Livermore and asked them to release that code because they wanted to simulate what happens if an airplane flies into a nuclear reactor dome. And so, Livermore released the code, made it, public source. And one of the French contractors then went to a German car company and said, "Hey, we could use the same code to crash cars." So that started the third-party crash code business. And now imagine if you're the author at Livermore, there are a lot more cars being designed in the world than whatever they do at Livermore. And so he's getting more external stimulation from the and so he eventually quit and formed a company. So did some other French people. So they released 3 codes that came out of LS-DYNA. Livermore Software did LS-DYNA, so they changed the name slightly just to distinguish the codes. And then in France, there was PAM Crash and Radios. PAM Crash is now owned by Keysight. Radios is now owned by Siemens. So these codes are still alive and well, and they're mainly used for occupant safety, which is the picture on the right, or the movie on the right. So that's a Volvo SUV. You can see like the airbags come out and the dummies go forward, and hopefully, the dummies are healthy afterwards. I got to tell you a great story. So Germany has something like the AAA, a car club, and their AAA actually has its own crash test lab, so they can smash cars and see if they're safe. So they've got some silly engineers working there, and someone got the idea that you can get a Lego model of a Porsche GT3 and take it to their lab and crash it. So they did that. And that inspired some other silly German engineers to think, well, if you can crash Lego Porsches, you should be able to simulate the crash of Lego Porsches. And so they did that. And then they decided they were going to have a Lego Porsche T-bone a Bugatti. And so, the guys at the crash lab actually did that. And, the Porsche was going 60 kilometers per hour. And so then this guys with the LS-DYNA code then simulated it. And that's a picture of the simulation. So these are the kind of important things that LS-DYNA is used for. Okay, so LS-DYNA has evolved a lot over the years. So one way it's evolved is just in what it simulates. So first it simulated, mechanical dynamics, drop something on the ground. But then, and that was for high energy, short time duration events. Like a car crash is, they simulate 50 milliseconds. That's enough to know whether you're going to survive or not. If you want to do metal stamping to make like the hood of that car, then you can imagine a tool and die set, and you stamp a piece of sheet metal, but when you take it out, it springs back. So in order to simulate that, you need to be able to take implicit as well as explicit time steps. And so LS-DYNA subsumed the Nike code, which was another Livermore code, And then over the years, people want to simulate different materials. And so more and more materials are put in, often by academic collaborators and stuff. So now there are like 300 different materials in the code. And it's become sort of a multi-physics code. So, and for, you think there's some incredibly hard, aeroacoustics problem that motivates this, but no. Mundane things. So if you think about a radiator, there's a structure and there's one fluid on the inside, a different fluid on the outside, and you've got heat transfer, right? Or I love these shock absorbers. There's a fluid in the middle of a structure, but this fluid reacts to an electric field. So if you want to stiffen your ride dynamically as you're rolling down the road, these shock absorbers can do that. So now you've got to have electromagnetics, fluids, and structures, right? So even simple mundane things require, multi-physics. I heard a funny thing from a guy at Procter & Gamble. They simulate the flight dynamics of Pringles because if the conveyor belt gets a little too fast, they take off and they fly around the factory, right? So, anyway, another thing is that when it started out, this sort of Fortran 77, for the first couple decades of its life, it was pure Fortran 77. Not a line of anything else was allowed in there. If you snuck in some C for a system call or something, it would be hunted down and deleted. Finally, they wanted to hire a mathematician, actually. And the guy said, I moved beyond Fortran, and they decided they loved him more than they hated C. And so C got in there, and now C++. And of course, Fortran has evolved. So the code has evolved itself. Okay, so the other thing that's evolved is I'll call, Thomas Sterling likes to say the execution model. So it started out, it was written for the Cray 1, or, a 7600 code was rewritten for the Cray 1. Then, it got ported to cache-based virtual memory systems, right? Sort of, late 80s, early 90s. Those things, came with multiple processors. So you had, vendor-based directives for, like the auto tasking for Cray, but, all the obvious vendors had, shared memory directives for, simple loop level concurrency. And then one day the founder saw another contribution from Livermore. Eugene Brooks's had paper on the attack of the killer micros. And so he thought, oh, I better start thinking about distributed memory. And so in 1992, before MPI, they hired their first guy to work on distributed memory. Actually shipped the initial like alpha versions of that code to GM and Chrysler in 98. And so again, when MPI became available, they switched. So and in that time period, it went from a Cray 1 to basically large, most users, big enterprise users are on large Linux clusters. So Titan was a particularly big one we were on once. Okay, so that was just a basic history of LS-DYNA and how it's evolved over time. Around the turn of the century, it was 1 million lines. Now it's over 10 million. So it's it's not just evolving; it's growing. Someone told me it's 15 million, but I don't know yet. So I work on a parallel direct solver, as Bronis mentioned. So I'll explain that in a minute. I'm going to just explain what I'm doing for a few minutes, and then talk about the fun stuff with OpenMP. A sparse direct solver means two things. One is it's a direct solver, which means Gaussian elimination, which my mom, the math teacher, tells me is an algebra 2 concept. So you all know it. 3 equations and 3 unknowns. Only, I might be doing 300 million equations, 300 million unknowns. And sparse means there are enough zeros to try and exploit them. So typically in one of these matrices, you start out with less than 100 non-zeros per row or column. Out of maybe 100 million, right? So there's a lot of zeros. You don't want to multiply by one because you already know the answer, and you want to avoid storing them, right? So that's what sparse means. And so very simple. If you showed Gauss 3 equations and 3 unknowns and one was a 0, he would have known what to do, right? This is a nice cartoon. Anyone who remembers Gene Golub, this is the way he used to like to illustrate. If you have a sparse problem, you want to reorder it to minimize the operation count on non-zeros, right, in the storage. And so the little cartoon here illustrates, here's an F rate, illustrates, when I eliminate row K from row I, then this 0, turns red for bad, it fills in. And if I leave this structure, like this arrow, Then when I eliminate the first row, they all fill in and it becomes a dense problem. Now it's n cubed work, n squared storage. If I just swap the first row and column beforehand, then it stays as order n storage, order n work, right? So clearly, in this case, you want to permute the matrix. And in general, finding an optimal permutation is, depending on what you're trying to do, NP hard or NP complete, and what you're trying to minimize, I should say. So it's impossible to, in general, to do this optimally. Oops, I could do this. Okay, so a little bit, again, the evolution. So there's a history of sparse direct solvers. When they absorbed Nike, I think it had a profiler. Livermore software license. There was a time when Boeing had a really good applied math or computer science group, arguably the best in the world, and they had a library, the Boeing Computer Services Library. An interesting thing is a measure of the respect people had for that is if you're trying to sell code in Detroit or Stuttgart or something like that, and you went to, speak to the head of computer aided engineering, say at General Motors, they would ask the trick question, do you have the Boeing code? And if the answer is no, then this interview is over, right? It was that simple. So the funny thing is Livermore Software licensed the code so they could say yes. Anyone who checked would see they paid the license, but they never actually integrated it because they didn't know how anyway. But they got past the trick question. Eventually, they started shipping MPI code. So now they needed to have MPI implicit. They needed a sparse direct solver. Thanks to Horace Simon, they came to me. So this now became a consulting gig for me. I paid my kids' private school tuition for many years. There are four basic steps. The first one is reordering. Again, trying to permute the matrix to minimize work. Then you do some analysis because you don't want to be studying some graph at runtime when you're trying to maximize floating point performance. Then you do the actual factorization, which, unless you've got many thousands of cores, dominates your runtime. And then triangular solves to get the answer. So I love this picture. So this illustrates the algorithm that we use for reordering, which is called nested dissection. Invented in the early 70s with Alan George. You would know. Anyway, so the matrix sort of follows the shape of the model. So in this case, it's the Rolls-Royce representative engine model. It's not a real engine model, so they can share it, but it has all the properties, so they can try and beat people over the head with it. So you cut it in half, and then you've got two halves. You cut them in half, right? And so this illustrates 3 levels of nested dissection. Chopping the engine up. Fun trick question. This is 2 different algorithms breaking up a Chevy Silverado crew cab. So trick question, which is better, to cut the crew cab vertically or to lift the body off the frame? Show of hands, who votes for vertical cuts? Come on. Who votes for lifting the body off the frame? Michael got lucky. So Metis does a better job than LSG part, which is our proprietary code in this case. And again, that illustrates it's an NP complete problem. It's hard for us too. If you keep recursing with this nested dissection, eventually you get something that looks like this. This is an elimination tree where the size of the triangle represents the amount of work needed to eliminate that part of the problem. This elimination tree correlates to this hood metal forming problem. At the leaves, you might have hundreds of thousands of leaves eliminating, say, 10 equations from 100. They're all independent, so you get a tremendous amount of task level parallelism. As you climb the tree, things get bigger, but they also get fewer. So at the root of the tree, you've got a lot of data parallelism. And so anyway, so you have to sort of blend those as you schedule that, which is another NP-complete problem. Anyway, so this cartoon sort of illustrates the algorithm we use. It's called multifrontal. It's almost 40 years old. Duff and Reed. So here's the nested dissection. You cut this little tiny grid in half. It turns out that the root separator can absorb one of its children, so it's absorbed 8. So that's why you cut it in half, but got 3 pieces. So this illustrates, the algorithm. This is the elimination tree. Here are the leaves. The corners of this grid are now the leaves of the illumination tree. The blue part is the factors you're computing. The green part are the so-called contribution block, the updates you're sending up the tree to your parent. If you think in terms of the BLAs, basically your algebra subroutines, this is factorization. We don't use this function, but you could. The off diagonals are TRSM, the triangular solve on a matrix, and the vast majority of the work is multiplying these two to update that. That's the dgem function, and this is illustrated as sort of a full matrix. In fact, I'm operating on symmetric matrices usually, so so we don't actually compute, or that might be ephemeral, but we don't keep it. Oops. Okay, so what happens if you have lots of processors? So back in the days of hypercubes, people started thinking about, well, I could give a branch to one processor of my hypercube, and I could give another branch, in this case, two small branches to another processor. And so we call it subtree subcube. The leaves are all independent, so nowadays, each MPI rank could maybe launch multiple threads, goes kind of sideways across the tree and pick up the leaves. So there's both data parallel operations low in the tree, I'm sorry, task parallel low in the tree, data parallel high in the tree. But the root of the tree is like the HPL benchmark, right? Factor dense matrix. Okay. Just for fun, for the MPI people, I went and I never call MPI directly. I only call anything once directly because I want to have, what if you link a library that's got 32-bit interface, but I have a 64-bit integers, right? So I only want to have to keep track of that in one place. So it's easy to actually count all the MPI calls I make because they're all in one subroutine, all the wrappers. And so this is a list of, all 53 that I use. I'm told you guys have several others, which I haven't found a use for yet. But anyway, just for fun, this has evolved over time. There's MPI 1, of course, MPI 3. I'm not sure if there are any MPI 2 ones in there, and nothing more recent. So in the spirit of evolution, there's a taxonomy. If you think of dense matrix factorization, people think of, there are 3 nested loops. You can sort of see 3 nested loops here. I goes down columns or traverses rows, J traverses columns, and oops, keep doing that. And then K follows the factorization. So you can change the order of these loops and then have a left-looking code where you update columns, or a right-looking code where you eliminate equations and then here propagate them forward. So there are different ways to organize this, and how you want to use that has evolved over time. So initially, so right-looking has the advantage of, if there's something wrong with the matrix, you find out right away and can do something about it. So originally these are right-looking codes. For the vectors machines, you just vectorize the I loop, the inner loop, maybe throw some zeros in there to maximize vector length. If you unrolled K and J by 2, that was enough to have asymptotic performance on your cray. So the idea of actually, so I always thought of math libraries, from academics, is they're great if you want to see how to actually, it's one thing to read an equation in a textbook, it's something else to see a working reference code, but you would never actually call the things, they're just, for reference. As you change, the one thing, the lovely thing about the Cray mainframes was they had more bandwidth than, they had more memory bandwidth than compute power. So by the late 90s, the cache-based machines, had more compute power than bandwidth. So you could, start unrolling these loops until you got in trouble with register pressure. I got as far as unrolling 6x4. Eventually, the vendors came out with SIMD instructions, SSE and ABX, and unrolled loops. Here we're getting, this is the old result of 10 gigaflops, whereas the libraries were getting 30 to 40. And so then just switch to a left-looking code, and use the library, and so the inner loops of the code have evolved over time. So the parallel loops have done something similar. So it's easy if you have, sort of like that root supernode where you have multiple processors. So each color could be a different, MPI rank here, could be a different thread. Apologize if they're not as cute as Amanda's, but the nice thing is I'm already working on panels because of the SIMD extensions. So this part's the same as the sequential code. I just have to keep track of, who owns what subset of the matrix and send some MPI broadcasts. Cleve Moeller of MATLAB fame told me in 1986 that, that's not going to scale beyond 100 cores or 100 MPI ranks. So eventually, when you're using a 10, that's fine. When you're using thousands, you have to switch to something like this. So here's a 3x2 array, or 2x3, I should say, array of you can imagine MPI ranks. And then each color could be a different OpenMP tile. And this is, again, sort of an old result, but here's what Cleve Moeller said. This is fine when you have a handful of processors, but eventually you have to switch to the tiled thing so that it improves as you add processors. And if you eventually this isn't good enough, and then you'd have to have a communication avoiding sort of three-dimensional thing, but we haven't gotten that big yet. Here's a result I'm really proud of. It's a few years old. This is joint work with NCSA, by the way. Rob Schreiber likes to remind people, if you think about the Linpack benchmark, it's not scalable. So we overcome that by just building the biggest possible memory and filling it with a gigantic problem. We, in some sense, with the Rolls-Royce engine model, we did the same thing. They got an Insight Award, so we were able to get on Titan. And then, thinking in terms of powers of 2, I needed 512 nodes of Titan just to have enough memory to bring the problem in core. And then as you add processors, the factorization, this is just factorization, your performance, improved out to half of Titan. There was a little hiccup in my load balancing, I think, not really sure. And this is basically 1 MPI rank per node and 8 OpenMP threads. So using both MPI and OpenMP to, use a national scale supercomputer. I'm actually quite proud of that. Okay, so what about GPUs? So, GPUs have been interesting for 2 decades. Even before NVIDIA came out with CUDA and IEEE arithmetic, I had friends working there, so I knew it was coming, right? So 20 years ago, I was interested in GPUs. So this is a model made by the UK Atomic Weapons Establishment for procurement benchmarking. And this chart here is showing, well, the blue curve is, well, how much work is there as you go from the root of the tree, down to the leaves of the tree. And you can see almost all the work is, in the big supernodes, at the top of the tree. Most of the complexity or structure of the problem is, down here at the bottom. And so it's an obvious thought, well, why don't you take these big ones and just put them on the GPU? So we did that, again, because the factorization dominates the runtime. If you can speed up the factorization, that's good enough to speed up the whole thing. First you offload the matrix multiplies and the triangular solves. And my attempt to do this died in the marketplace because our customers' models were too sparse. And that's remembered as a black mark against me. A funny thing is, there's a company called Ansys. I was consulting for them and Livermore Software at the time. So Ansys had the same code. Livermore Software paid for the CUDA, so we didn't give it to Ansys, but they were smart enough to reverse engineer it and write it themselves. And so, the first attempt was mine, failed in the marketplace. The second attempt was of theirs, also failed for business reasons. The third try actually went to market in 2010. So it took 2 or 3 years to get it right, and to find customers that had the right model. Eventually, LS-DYNA didn't get on GPUs, but Ansys Mechanical did, the original Ansys code. Okay, all right, so now revisiting GPUs. So what's changed? Well, now you've got unified memory. I don't have to write in CUDA anymore. I've got OpenMP. I've got multiple vendors of these things, and with not just unified memory, but the packaging and high-speed networks, less latency, everything is better than it was. And so why would we consider OpenMP? So the code was designed and architected for a SIMD machine. So you might say it's slightly different that, the Cray wanted, say a 64-bit long vector, it really wanted longer for the compiler, but, we can pretend it's 64. The GPU's about maybe 64,000, right? But still it's in theory, it's SIMD, so it should be straightforward. We've got a lot of code. We have 300-ish materials. They're 1, 2, and 3-dimensional now IGA versions of all these things. A few thousand lines a pop. You multiply that out. There's millions of lines of code. You can't conceive of rewriting millions of lines of code in CUDA and HIP and SYCL, and then whatever comes around tomorrow, like I don't know about yet, right? On the other hand, we have a great history with directives. We vectorized, using this, ignore vector dependency directive, 40 years ago. And that worked fine. Similar directive helps compilers today fill pipelines. So the open question is, well, could you use an OpenMP directive and target a GPU as opposed to having to rewrite the code? So, and I insist on OpenMP, not anything else. I'm worried about, I want to work with the standard. I want to know that I can port to a variety of targets and I can continue to do so in the future. So I have colleagues who aren't so fastidious and they think, well, but this is better today. So anyway, so here's the fun part. So there's a tool called Perfetto. So if you use AMD's RockBLAS, you can get a log and then you can visualize 75 cube of solid elements. So it's not a real model, it's a pretend model. The reason for choosing this one I'll show be obvious later. And so here I got 2 MPI ranks, 1 thread. I'm running on 2 cores and an MI300A, using Michael's compiler. And if you look, it starts here, ends over there, 581 seconds, of which 90% of the time is in this burnt orange factorization, right? So I told you it dominates the number. Oops. If you look over here, there's this olive colored part. This is the root supernode, and that's the part where there's some relatively tight MPI interaction. So, so we're going to drill down on that, and you can see that, well, G is for for gem, for GEMM, the library call for matrix multiply, and there are 36 of them here, 35 of them here, and you can see each of these, light blue is like a second of real time, so they dominate the runtime. This is processor 0, or MPI rank 0, I should say. So here it's it's waiting for a broadcast. Here it eliminates a panel. That's dominated by the DTRSM call. And there are these little blue lines here that are creating, it's a symmetric problem, so I have to create an ephemeral part of the upper triangle. So you see there's a, that's what the little blue line is. Anyway, so the first obvious thing is the runtime is dominated, by design by calls to the math library, right? So could we offload that? These are, tend to start out as, academic open source things, then the vendors optimize the hell out of them, first for CPUs and then for GPUs. I think MKL's buried these in the same library. Intel's buried it in the same library. So the calls aren't exactly the same. This is the AMD version. Number one, there's this silly handle thing, which, doesn't belong there. And these should be characters instead of integers. And I shouldn't have to tell my Fortran compiler that these are pointers. So I actually find this kind of annoying. So if you, and there are thousands of these kind of calls. And so you don't want to go through, thousands of lines of code and say, if GPU do this, else do the normal code. And so a good thing is libraries, as far as I know, starting with IBM's ESSL, NBBLAS, or Michael's AutoBLAS, all bury that call. So you make a normal looking call to the math function you want, and the library says, how big is this? Is it big enough to give the GPU? And that decision is transparent, and you don't have to muck with your code. So anyway, if you do that, then here's the same problem. Now instead of 580 seconds, it takes 102. So all this stuff like parsing the input deck that I'm ignoring, suddenly non-trivial. Though in fairness, normally this is for mechanical dynamics, so you do not one of these, but maybe hundreds. So it still disappears. The reordering is not offloaded, so now 10 seconds is noticeable. And the burn orange here is down to 50 seconds. So we got basically a 10x improvement in runtime just by offloading the library. And this is drilling down. Here's that broadcast, and I don't know, this was, waiting on the broadcast was 89 seconds. Transmitting the broadcast was 20 seconds before. Now it's faster, and I have no idea why that is. So that's some MPI magic. Maybe somebody can tell me, afterwards. But that little blue bar is suddenly, a visible end-off fraction. The DTRSM, which dominated this, is now small, but here's some Fortran code, which is now the new end-off fraction. So we have to go further. Okay, so offloads. This is bring back happy memories of Bronis of his youth. So green phosphors on a black CRT screen. This is that same sort of blue bar. The good old-fashioned Fortran. Basically, I'm taking a panel of the lower triangle, I'm transposing it to make a panel of the upper triangle, and I'm scaling it. So all you need to do is add this directive, and it automatically offloads one. So this is wonderful. Sort of the best case. It's not always quite this pretty. So here's a slightly different thing. This is a PAX triangle. So I'm going to walk through it, kind of one word at a time. And I'm taking it and I'm scattering it into a square. And the lower triangle is square. So this one loops 1 to n. This goes from j to n. And here are the relative index vectors. So I get the row and the column. A problem is the Cray vector compiler could figure out p here. But OpenMP can't compute p on every thread, tens of thousands of threads. So right now, what I have to do is I could still have my, basic loops, except these loops have to go 1 to n. So I have to have an if to tell half the threads go to sleep. And then I have to compute my address as opposed to just, auto incrementing it. It's not an impossible transformation to make. You wouldn't want to do this on the normal processor. So now you're going to have, if no GPU do this, else if GPU do that. But then the directive, offloads it, and it still speeds up tremendously. You wouldn't want to do millions of lines in this. A few thousand here or there, isn't too much of an overhead. If you do that, now this is getting bigger. That's still 10 seconds. I've done two things here. One is I've offloaded stuff with OpenMP. The other one is I've offloaded memory allocation now with OpenMP. So allocating the storage on the GPU directly with this target alloc. And then there's a funny thing where yesterday, if you saw the tutorial, Michael talked about the need to if I have allocate on one, if I have memory on one on the host or I have memory on the GPU, they have to know about each other. So here's the host learning about the memory. But now this factorization is down to 5 seconds, right? Down from 500 to 50 to 5. It looks like 7 here because of all the tracing. So if I drill down on that, and again, I don't understand this part. MPI has gotten faster still. So now it's down to like 1 millisecond, whereas this was 20 milliseconds when it was just the two host, two MPI ranks in the standard compiler. The speed up here is like for the matrix multiplies is hundreds, right? This is 2 milliseconds instead of 1 second. So speed ups of 400 to 500 on the matrix multiplies. Now I've offloaded. Here's forming the ephemeral part of view. Here's finding the max off diagonal. So suddenly, DTRSM is visible again. So there are still parts of this that are not offloaded. The Gaussian elimination itself is not offloaded, for example. I haven't figured out how to do that properly yet. I may end up having to cave and write some hip, but it works. And so then just to know, like, how does this perform? Just, sanity check. Is that a good number or not? So MUMPS is a French open source code similar to MF2. I bet one of the guys who's an author in 1988. So these guys are very senior and smart. So here they're in 1 GPU on a Grace Hopper, 48 threads because their OpenMP is better than mine. I would never do that many threads. And it takes them 9 seconds. cuDSS is a GPU native solver being written by NVIDIA. Same Grace Hopper machine, 5 seconds. If I run 48 MPI ranks 2 threads on my solver, MF2 means second generation multi-frontal. This is on a Sapphire Rapids, so kind of a normal computer for reference. Almost 15 seconds. This is the code I just showed you, this, and the reason that I picked that model is that that's what these guys did. So again, 5 seconds. So, I think that's a good, it's not the same computer, it's not the same operating system, it's not the same compiler, but they're all contemporary. And I think, that's a good number. And I have 4 sockets, so if I use more of them, it gets faster. There's not enough memory to do this bigger model. So the French guys didn't bother with it. This one would have been fine, but they didn't buy, they couldn't, there's not enough memory to do that, so they didn't bother to run it. Here it is on my Sapphire Rapids. This looks horrible when you look at it, my God, 700 seconds. But I think that's a good thing because this is a real production code. It's been evolving for decades. It's got precision arithmetic, low-rank approximations, and it goes out of core where you don't have memory. So it just transparently went out of core. I must have gone for coffee because normally I would have stopped it when it taken so long. I wonder what the bug was. And if you get a big enough machine to bring it in core, then this is a bigger problem. So the difference between this and this is now over an order of magnitude. That's about 47 teraflops. You like to think about flops instead of time. These are 2 procurement models from this is the Atomic Weapons Establishment again, and this is Rolls-Royce. So here, this is now 4 sockets of MI300A. I can use 2 MPI ranks and they can effectively share the GPU. That's why I've got 8 here. This is 53 teraflops. This is almost half the peak performance that a national scale supercomputer got 10 years ago. I find that just extraordinary. Just to compare it, I'm sorry?
I said it's crazy.
It's amazing, right? And so here's a very nice IBM machine. I think it was 8 sockets, 4 terabytes of memory. It got 8 teraflops. A brand new, I think it's called Granite Rapids from Intel, 7 teraflops, right? So this is if you fit in a sweet spot, we've got a nice 3D model, not too much memory. This is extraordinary. This model, it's 3-dimensional. It's made out of tetrahedron, but the thing it's modeling is pretty 2-dimensional, and so it's here the peak isn't as high. Having said that, I think there's at least another factor of 2, in here. So this is going to get better. Okay. There's other stuff that LS-DYNA, 10 million lines of code moving one thing isn't going to help very much. So there are other people working on other stuff. So and if any of these fail, if any of these top 3 fail, then we're probably dead in the water. But as far as implicit for linear algebra, I think that has succeeded. Okay, the fun part, what I want you to do for me in the future. So for the MPI people, I have 2 requests. One is, if you look on GitHub, Miller-Maley's put up these things called conveyors. There's a push-pull model. I don't want to send one word to some other processor that's ridiculous. I want to just push it and then have the library queue these things up and aggregate a big message and transport it. And the other guy can pull, and Miller's implementation, which he calls conveyors, sort of maximizes injection bandwidth. So he's not worrying about minimizing latency. So if you've got a bunch of stuff, send it with maximum bandwidth and it'll get there, like I said. So at least do that. If you think of something better, that's even better. Also, it's always annoyed me that they can have MPI any source or MPI any tag, but there's no inverse to that, right? There's no symmetry, and it doesn't have to be that way. So there's another communication standard. It's an actual standard, an IEEE standard. The high-level architecture. It has a runtime interface, RTI. It's an MPI, and they have interstitial communication. So if you're in a tree in the woods and you fall down, you send a message, "I fell." And if no one cares, the message is never delivered. But if someone does care, then the communication infrastructure keeps track of who cares about the tree. So there are ways you can imagine, creating the inverse of that and adding proper symmetry to MPI. This is another thing. There was a Gen Z attempt to have a global address space. Now there's Compute Express Link. I've been writing message passing for almost 4 decades. I much prefer shared memory and program abstraction. I can't help but wonder if you could use, CXL or something like it and create a better, not an MPI2 shared memory abstraction, but a real one. And just to be provocative, I'll say, if you did that, could OpenMP displace MPI? I mean, I think the answer is as soon as Fortran goes away, that's when MPI will be threatened. But could I write new stuff in this, in a global address space that might be preferable? That as long as it coexists with the existing stuff, and that's just the same as C++ and Fortran. I was hoping to get some fights going on that. Just for fun, I'm programming in Fortran. I like to say I don't program in the languages that are younger than I am. I've had contemporaries. If I worked for a bank, maybe I care about COBOL. But I am seriously interested in, what's the future beyond, say, C++? What are you guys doing for Rust or, other contemporary languages? So just a question. I'm trying to use OpenMP to get on accelerators. The space of potential accelerators is getting bigger. It's not just GPUs. So just some examples. Cerebra, I love this. These guys have gone wafer scale. GNAM all tried and failed. So it's, people tried for decades. These guys have finally succeeded. Could I use it for something? We actually have a CRADA with a DOE laboratory. We did some benchmarking on simple, rectilinear sparse matrix stuff, and it was outrageously fast. Of course, it's very hard to imagine creating a rectilinear sparse matrix for me. So I need an unstructured one. Nettle's working on that. If they succeed, I can see this as an accelerator for several of our codes. How would I use this thing? One thing is the programming model is really primitive. So, could you guys help with that? Another thing is it's not going to be attached on a PCIe channel, and it's going to be like Google TPUs across the network. And OpenMP or MPI give you an abstraction for dealing with this huge remote accelerator, and driving it from a cluster, not from one core. This is conjugate gradients, which is probably familiar to a lot of you people, except written as a data flow graph or a streaming engine, because I'm old, I call it data flow. There are 3 stages, and then dependencies break the stages up. Here's matrix vector multiply, sparse matrix vector multiply, which dominates the complexity of the whole thing. This project started out by saying, well, I can have HBM on my FPGA, so I have more bandwidth. Could I make an accelerator that's more bandwidth than the host? Could I make an accelerator out of it? The bottom line is that it's not faster than a GPU, but it's cheaper and it's lower power, so you already it's more cost effective. It's not that much slower. So, how are you guys going to help me deal with that, right? How is OpenMP, for example, going to deal with, an accelerator that's not a GPU and maybe an ephemeral thing? And the same question for MPI. It's not a homogeneous, device anymore. And this is the postdoc who did this work, named it after the California state bird. So I mentioned reordering is a problem. It's NP complete or NP hard, depending what you're doing. It's recursive graph partitioning, which is also NP hard. You can reformulate that as an Ising model if you're a physicist, or unconstrained binary optimization if you're a computer scientist. And there are accelerators for these things. So E-Wave has its adiabatic quantum annealer. Open System is physics for noisy. That inspired Fujitsu and Toshiba to make basically simulated annealing in silicon. And there's this thing called Light Solver, where they're trying to use lasers interfering with each other to, again, create an Ising model. This is an example from, the Light Solver people. We gave them the role, actually Rolls gave them their Rolls-Royce engine model. This is the first cut in the nest dissection. This is a 20% reduction. And these are coarsened grids, the Sandia idea. So this is Metis, which was better than LS-G part before on the pickup truck. Using Light Solver, it's a 20% reduction. I'm doing Gaussian elimination, that's 0.82. It's almost half the work. At the top of the 3. Overall impact of 7%. So this is a research project that's really resulted in project. And finally, a quantum computer. This is IonQ. They're implementing variational quantum time evolution. Quantum die. It converges with time. Here, one thing is the algorithm has 1 qubit per vertex in your graph. So now you take the 200 million, equation Rolls-Royce engine, maybe bring it down to a graph of 10 vertices or 28, which you can simulate on a quantum computer. An interesting thing is, then the red line is our classical heuristic. There are data points that are, better than our classical heuristic. In a couple of years, when they have, a big enough computer to get out here, they're still getting points better than our classical heuristic. Then, now we've got something to take them on. So I can help you that. All right, finish. I mean, you know, there are lots of codes that have been around for a long time. They're not going anywhere. And partly because they're evolving. You know, parts of the code are really old, but most of it's not. You know, they're living in, you know, building on an ecosystem of stuff that you guys are creating for me. And OpenMP and that, you know, they're not the only parts of the ecosystem, but OpenMP and MPI are important parts, which I think are going to get more important as you help me do things like GPU offloads. So, done. Yes.
All right, good. All right, questions? We have a little bit of time for questions.
Thank you for the interesting talk. What sparse storage schemes do these various solvers use?
The matrices come in sort of a normal, you know, compressed column kind of, you know, that's what the input looks like. The storage itself is sort of customized. Typically, if you have like,
What I meant was first column, first row, or triplet.
the first one. And if you have
So IJ arrays, value array.
I have a pointer to column, then I have a row index, and I have a floating point value. And if it's an unsymmetric matrix, then I think of it as a chevron, and I have one row index, which is the column index in the upper triangle, and then, you know, one integer and two floats. So a pointer for a column or a chevron, an integer and a float, or an integer and two floats.
Yeah, so that's compressed column.
I'm sorry?
That's compressed column or compressed row.
Well, it's symmetric, so it could be either. I like to think of it as a column, but my French friends think of it as a row, but it's the same. And again, we assume if it's unsymmetric that at least the pattern is symmetric, and then I can have the number of indices. But then inside the factorization, that's the custom storage format. And because it's been evolving for years, you know, there are multiple such formats depending on the machine you're targeting.
Other questions? All right, well, I'll ask one. So first of all, you said you hide all of your MPI inside of a wrapper. And then you also talked about some complexity with porting some things because you have lots of stuff spread all over the place. So like using CUDA or something like that would be difficult. And so I'm curious if you're familiar with like Cocos or Raja and the C++ abstractions that basically allow you to identify patterns and then apply execution models. And
Yeah.
do you wish Fortran has something like that?
So for new code in the, you know, future, sure, that would be useful. A funny thing is we have at least, you know, not codes I work on, but we have at least two codes that are C++ where they've essentially created that same sort of framework because, you know, people talked about, you know, Raja or Cocos before it existed, right? And so, you know, we had a need for it and essentially created it for ourselves, right? And so, you know, I'm not using that, but other people are using those ideas. I take that back. There is some C++ in Dyna, and I'm sure I think they're using Cocos. So it has crept in, but it's not in a corner I'm familiar with.
All right, we can have maybe one more question if somebody's got one. All right, well, let's thank Bob again.
Thank you very much.
All right, thanks, Bob.